Hello, this week we're diving into RLC circuit in AC current. So I'll solve problem 27 from Randall and focus on resonance frequency using the Grada model to explain the logic of the circuit. So here is given only one thing, that the frequency equals to 200 kilohertz, and we know the formula, like since it says that it's resonance, we know the formula for omega. The simple formula one is 2 pi frequency, and the formula for resonance is 1 divided square root of LC. So we're just equalizing this to each other. 2 pi frequency 1 divided LC, and here we can easily find frequency, where it is 2 pi LC squared. So let me start using Prada model. Let's start with pattern recognition. So first, pattern recognition. I recognize that resonance occurs, how I said before, like resonance occurs when the inductive reactance and capacitive reactance cancel each other out, which means they're equal to each other. And the key pattern here is that the frequency depends only on inductor and capacitor. So yeah, how I write here before, the frequency depends only on inductor and capacitor. So resistor is part of the circuit, but it doesn't actually dictate the timing of the oscillation. So yeah. So next thing is decomposition. Using decomposition, I break the problem into two independent scenarios. Like in case A, where we modify the resistance, we are doubling the resistance. And in case B, where we modify the capacitance, this our capacitance becomes doubled, and this allows us to see how each component independently affects the system's heartbeat. So the next thing is abstraction. Now let me write here. This is the most important step for this task. I don't need to know the actual values of like inductor or capacitor. I can abstract the formula into a relationship, like frequency is proportional to 1 divided by square root of capacitor. This simplification allows us to solve the problem without any complex calculations. Like our frequency is proportional to 1 divided by LC. We're just ignoring like resistor for frequency, because how I said before, the key pattern is here about like inductor and capacitor. Yeah. So the next step is algorithm design. Algorithm design. So my algorithm is simple. For case A, we just check if resistor is in the frequency formula, if like resistor is changing is changes, just if new one, the new frequency will be equal to the this one. In case B, we're just substituting the new C into the proportionality and calculate the change factor. So our new frequency will become the initial frequency divided by square root of 2. We're just putting like this one here. So let me go to the calculation part. In case A, since resistor is not in the formula, the frequency remains the same, so our new frequency will be equal to initial frequency, which is 200 kilohertz, which means it stays the same. And in case B, our new frequency will be equal to 200 kilohertz divided by square root of 2, which is approximately like 141.4 kilohertz. So the last step is data analysis. If we will build, I'll show the Falstead, the circuit in Falstead, and I built an RLC circuit and double the resistance. The peak stays the same. Just let me show the Falstead at first. So here you can see the simple Falstead circuit. I used AC circuit, how it says in the given OS task, and I have resistor, I have inductor, I have capacitor, and I just put the random numbers, so it doesn't matter, like, yeah. And now let's verify our theory with a Falstead simulator. Here, like, if I will double the resistor value, you should watch the oscillation, the graph. I'll double it, and as I increase resistors, the peak of the curve becomes lower and wider, and this is called lower Q factor actually. However, look at the position on the frequency axis. However, like, the peak didn't move, it's still exactly at 200 kilohertz, but in our case it's 60 hertz, so it doesn't matter. Like, so this confirms our abstraction step. Let me bring it back so you can see that it remains the same. Look at the green line and how you can see it remains the same. And the next step is we need to double the capacitor value, and let's check what will happen. Okay, 20. Now look at the graph. The entire resonance curve shifts to the left towards to lower frequencies. If we will check the new peak position, and now it's like, so let me So yeah, if we will check the new peak position, like it gives us the lower frequencies that we had before. So this perfectly matches our algorithm's calculation of frequency divided by the square root of 2. This simulation proves that frequency is only sensitive to inductor and capacitor, and our product model successfully predicted the like behavior of this RLC circuit. And that's it for today. Thank you for watching.